Hey there, curious minds. Ever wonder why some sounds are so low we can't even hear them? Here's a fun fact. Infrasonic waves are the sneaky sound waves with frequencies below what our ears can catch. That means anything less than 20 Hz. Imagine sound waves moving so slowly that your ears just shrug and say, "Nope, not hearing that." Because these waves have such low frequencies, their wavelengths become huge, really, really huge. Picture waves so long, they need gigantic sources to create them and big, solid or dense materials to travel through. This is exactly why a tiny violin string can't produce infrasonic sound. You need something bigger and stronger. Now, let's bring in the physics friend we all know, the wave speed formula, which says speed equals frequency multiplied by wavelength. In symbols, that's V equals F times lambda, where V is speed, F is frequency, and lambda is wavelength. Since frequency is super low in infrasound, wavelength stretches out accordingly. And cool thing? Because of those long wavelengths and low frequencies, infrasonic waves can travel really far without losing much energy, especially through dense materials like earth or water. So, the next time an earthquake rumbles, remember, it's these infrasonic waves silently zooming beneath your feet. Let's talk about where infrasonic waves come from. Both nature and humans love to make these deep, low-frequency sounds. Mother Earth's biggest shakes, earthquakes, and volcanic eruptions are awesome natural infrasonic sources. Even giant ocean waves or tsunamis generate these slow-motion sound waves like the Earth's own heartbeat. But wait, animals got in the game too. Whales and elephants use infrasonic calls to chat over great distances because when you're that big, shouting loud isn't enough. You need those low-frequency whispers that can travel miles. And severe weather, like tornadoes and fierce, howling winds, join the party by producing infrasonic waves as well. On the human side, our heavy machinery and engines rumble and vibrate at low frequencies, creating artificial infrasonic waves. Remember, if a wave's frequency is less than 20 Hz, bingo! It's an infrasonic wave ready to travel far and wide, often unnoticed by our ears but very real in the physical world. Alright, now let's dive into how infrasonic waves get around. These waves are like the marathon runners of sound. They work harder when the path is solid or liquid. That's because infrasonic waves travel much better through solids and liquids than air. Think of it this way. In solids, particles are packed closely together and spring back fast, perfect for carrying these giant sound waves. Their speed actually depends on the medium they travel through. In solids, infrasonic waves zip faster than in air because solids have a higher elastic modulus, which basically means they're stiffer and bounce back quicker. And here's a neat formula for you. The speed of longitudinal waves in solids equals the square root of Young's modulus divided by density. Mathematically, that's V equals the square root of E over rho, where E is Young's modulus, a measure of stiffness, and rho is density, or how heavy the material is in a given space. Now, how do we catch these inaudible whispers? Since humans can't hear infrasonic waves directly, we use sensitive instruments like microbrometers, which detect small changes in air pressure, and seismographs that record ground vibrations. While these waves are mostly silent to our ears, they're not completely harmless. They can cause vibrations that you might feel as a rumble or even physical discomfort. Imagine your house slightly shaking during a big storm or an earthquake. That's infrasonic energy at work. Scientists use arrays of these detectors to locate where the waves come from and figure out how powerful they are. And that power relates to the wave's amplitude. The energy transmitted by a wave is proportional to the square of its amplitude. In other words, if amplitude doubles, energy jumps by 4 times. Imagine infrasonic waves as invisible superheroes, silent but packing a punch that's all about amplitude squared. You might not see or hear infrasonic waves, but they're superstars in science and industry. Geologists use infrasonic sensors to get early warnings for earthquakes, detecting these waves before the faster, shaking P waves arrive, kind of like catching a storm before it hits. The military and space programs also rely on infrasound for tracking missile and rocket launches because those big engines make lots of low-frequency noise we can sense from far away. Here's a wild fact. Elephants use infrasonic sounds to chat across several kilometers, talk about long-distance phone calls without any cell towers. Finally, medical researchers study how being around infrasonic waves for long periods might affect our health and brain functions. So infrasonic waves aren't just physics fun, they're practical heroes in keeping us safe and connected. Let's put our knowledge to the test with a quick example. Suppose you have a sound wave vibrating at 12 Hz. The question is, what kind of wave is this? Remember our rule of thumb, if the frequency is less than 20 Hz, it's an infrasonic wave. Since 12 Hz is definitely less than 20, we classify this wave as infrasonic. That means this sound is too low for humans to hear, but it still travels through the earth and air, doing its secret deep sound business. Checking back, our condition F less than 20 Hz is perfectly satisfied. So, next time you find yourself near heavy machinery humming low and slow at 12 Hz, you'll know you're in the world of infrasound.
Alright, let's wrap up our infrasonic adventure. To remember, wave speed equals frequency multiplied by wavelength. V equals F times lambda. And when frequency is less than 20 Hz, you're dealing with infrasonic waves. In solids, their speed depends on the square root of Young's modulus divided by density. V equals square root of E over RIO. Energy carried by these waves grows with the square of their amplitude. These waves love traveling through solids and liquids and come from impressive sources like earthquakes, volcanoes, engines, and explosions. Plus, animals like elephants have mastered infrasonic communication miles away. Scientists and engineers use these waves for important jobs in geophysics and defense. So, even if we can't hear them, infrasonic waves play a huge role in our world. That's it for today's concept. Remember, physics is fun when you can laugh and learn. See you in the next session.